All right. Thank you very much, Greg, for the introduction. So I wanted to thank Survey for the opportunity to talk here first and the ability to reschedule a talk as needed. And then second, as Greg mentioned, this talk is on behalf of Jack, who would really have liked to be here. He couldn't be this opportunity, but he'll look forward, I believe, for the next time. And then third, this is material I'm going to present here within the collaborations of Roses mainly for this talk, and Lucinite as well. So I'm going to discuss here again the dawn of radio astronomy from the moon. So these are exciting times in the direction that Greg was presenting before. And we have great opportunities, as we've been hearing during this forum, in terms of Artemis and the CLIPS program. And again, as we heard as well from NASA folks in general, the programs keep going strong. So these are positive news. Again, both Artemis and CLIPS program. There's a lot of exciting things that we hope that are going to keep happening. And for this talk, I'm going to focus on the commercial lunar payload and services, CLIPS, that we've been hearing as well during the conference. And in particular, I'm going to talk about the IM-1 mission that was carrying, again, this first radio telescope from the moon called Roses. You can see here within the fairing of the Falcon 9. And we see the housing of the antennas, the 4 monopole antennas that make measurement from the moon, as I'll mention in a moment. So I want to tell a little bit the story of this lander, which is a story that it's in retrospective, accomplishes his namesakes in the terms of this is an odyssey. There was an odyssey to get to the moon and to make the measurements. So Odysseus achieved to do that. They started the launching in February 2024 and the landing as well. And here we can see a little video. Okay, yeah, thank you for, or maybe automatically went on the video. So you can see here Odysseus how it detached from the Falcon 9 and starts his travel to the moon. Okay, so this travel was not free of things to solve, opportunities to learn, I guess, for the intuitive machines folk. And one of them, you can see more details in the paper, but one of them started already in transit, right? So due to some issues in the rotation, there was one side that was overheating, and one of our antennas deployed accidentally in transit instead of on the moon. So this is antenna D, you can see here. But fortunately, we could take data in transit, and actually, as you'll see, most of the data is from this antenna in transit. So this is the landing site, Malaper 8 on the South Pole. And then we can see here how Odysseus is approaching landing. This is from a photograph taken from a payload on the IM-1 mission. And then we can see here the landing. That was another notable issue that was due to another technical problem in deploying the proper landing system for Odysseus that caused a rougher landing than expected. And we can see here the broken leg of Odysseus in the landing, which end up being tilted on the moon, as here the CEO of IM-1 is showing up, and we can see the picture from intuitive machines as well. So this causes the problem that you have two issues here, for power, right? So the solar panels are not in the orientation expected, so you have less power that initially intended, and then you have also a problem with communication. The high antenna, the main antenna for communication with the Earth was pointing to the ground, I believe, and it was difficult to transmit data on the ground. So there's also heroic efforts for IM-1 to do that and to share the data between the different payloads, the data that they could collect from the moon. We have data from 2 days, LS1 and LS2 from the moon and the lunar surface, in addition to the transit data. This is where Odysseus landed up. This is a nice picture from the LRO from Odysseus on the lunar surface. And then this is the collaboration from Roses. Before I started, this is some of the details, right? And this is, again, another choreographer for the science team, and in this case, for one of our students that recently graduated, Joshua Huber. This paper is submitted in a good shape on the review, and he designed this cleaning process that you can see here from the data, what we call the digital signal process data. You'll see two types of data, the DSP data and the waveform data. So these cleaning processes involve removal of the noise, the decontamination, another type of noise as well, linear noise, a calibration to voltage, and final transformation to a power spectral index, density. Right, so this is a complicated process that was developed for this purpose, and you can see here the result of the process. On the left, you can see the uncalibrated data. This is for one of the antennas, the D antenna in transit, the one that was deployed, right? So this is the one that we have more data. And actually, interestingly enough, that antenna is the one that on the lunar surface was crashed. So we don't have data from this antenna on the lunar surface. We only have it in transit. So, and then the other three antennas have data on the lunar surface. Here we can see the cleaning process on the left, and on the right, after the data is cleaned up, you can see some clear lines. So those lines we think that are signatures, radio interference from the Earth. So we're seeing the Earth. This is interesting as well, actually, so we call it technosignatures, right? So this is the kind of signatures that you would be interested, for example, to see in radio for exoplanets and try to infer if there is a technological civilization there. So we know that it is on Earth, and we detected that here, right? So this is on the lunar surface on the second day for antenna B, the same, uncalibrated and calibrated data. And here are the three views from in transit, as how you see the Earth from Odysseus or Roses, actually, in transit for the first day of observation, LS1, LS2. And you can see here Roses Odysseus tilted and the four antennas. The D is crashed on the ground, we think. And here again, the four antennas, D does not have black dots because this is data from the moon. The black dots is waveform data. This is the other kind of data that we analyze. And you can see that the red is tested data from the ground on Earth. So this is basically electronic noise and systematics. And we can see that there's some signals that rise above that. I'm pointing two of them. Again, these technosignatures that I was mentioning. This is Earth, some probably powerful transmitters from Earth. And then we can see also the DSP, the other kind of data that I mentioned in cyan and in gold. All right, so in addition to the technosignatures, another important thing that we observed from the moon, we detected our galaxy. This is one of the main things that we want to do towards cosmology. Cosmology that Greg was referring, astrophysics is breaking through science, but before we need to deal with the galaxy, which is very bright, right? So we see the galaxy here with this very small amount of data. Again, a very immense effort by Joshua. He applied very sophisticated techniques, Bayesian techniques, and cleaning techniques from a paper Switzerland Lug, which we adapted here. And we can see the detection of the galaxy. This is this dashed line is the reference from the fiducial galaxy isotropic spectrum from Novacco and Brown. So we see it from the moon, from these constraints here, and then we also can measure some parameters of the antenna. All right, so this is a very interesting detection from this first experiment with very small amount of data. This is basically 5 minutes of data for this detection with waveform data. All right, so this is some of the lessons that we learned. So we need to be, make sure that the actuator doesn't, deploys the antenna before time. We need to better calibrate gain variations. We need to shield from interference. Again, that was a very quick experiment that was put together for other purposes initially. And then we utilize it for this purpose here. So we know that we need to do all these things. We want to do polarization as well in the next experiment, and we're going to use the beacon that I'll point out quickly for Lucy 9. So this is, again, for Roses 2, but before that, we're going to have Lucy night. This is going to be on the far side. All what I talk about now was in the near side. Remember, we're seeing Earth. On the far side, we will not see Earth. We want to be protected from radio interference from the Earth to the astrophysics and cosmology. So this is Lucy night, and I'll point you to the talk yesterday in the astrophysics session from the PI, Stuart Bale. So here just wanted to present quickly the team and put the picture, and just want to quickly only say one more thing that, okay, I'm going to put all that quickly so you have the full picture of that. So we're going to use a real-life satellite, the one that's going to send us the data back to Earth from the lunar, from the far side, to calibrate the antenna, right, to up to a better level that we could without this data. So this is the technique that we're going to use. The beam of the antenna is critical for our purposes. This is a pathfinder, so we'll probably have basically better measurements of the galaxy, very good measurements, the best measurements of the galaxy in this very low frequency, and potentially the signal, but if not, that's okay. We'll keep going on to that. Again, this is a pathfinder. This is going to give us very good information for keep doing the work to, analyze all these systematics and then hopefully have the big cosmological signal potentially in this one, or if we're lucky here. So I just want to finish to summarize there's a bright future for these CLIPS missions, starting with ROSES. 2024 with next year, 2026 Lucy night, as I'm pointing here, and then 2 more CLIPS missions. If you saw the talk from Stuart as well, there's a sister experiment, Lucy Light, as well for 2027, and ROSES 2 that I mentioned before on 2028. So we're very excited about all these CLIPS mission programs and possibilities with Artemis. We have a lot of more ideas could keep going, so there's a lot of interesting opportunities to follow up. Thank you.